All right, ladies and gentlemen, now we're going to start this very last section of Chapter 10, which is going to be focused on what I would call uh, an application to some of the stuff that we've been learning about geometric and arithmetic sequences in series. But this one's going to be about the expansion of a binomial. That's going to be in 10.5. Again, we'll skip past any of the review questions, and we're going to move down here to something that I think you've probably done in the past. Now, let's talk about a very common mistake that maybe you might have made when you were back in Algebra 1. All right, now a real common mistake that you're way past at this point in time was that mistake of if I gave you x plus y and I told you to square it, and then you just applied that actual square on each one of these two things, and you came up with x squared plus y squared. Now, you're not making this mistake anymore. And if you are in pre-calculus, then you really need to get it under control. Okay, what you need to do in a situation like this is that we end up learning back in Algebra 1 that we should at least FOIL these particular kinds of ideas. Now, FOIL, for the most part, in Algebra 1 does a really solid job of actually teaching you how to fix this particular deal. However, when the power starts to get bigger than 2, like 3, or even higher than that, then the FOIL really starts to get super, super tedious. And what we'd love to have is we'd love to have an easier possible way to do these things. So I'm going to do an old-fashioned one just as a reminder of what this foiling concept boils down to. So this would really mean, since we're past that common mistake from Algebra 1, that we would write the x plus y, we would write it 4 separate times. Okay, now some of you, it will be very hard for me to break you out of this box. You'll be like, I'm just going to FOIL, G. I'm never going to learn how to do this thing. But then by the end of this assignment, I will have broken you. And just like a horse, I will break you, and I will be able to put a saddle on you, and I will make it go the right way. Now, if we do FOIL on this, we're at a point in our careers where we could actually FOIL these two things together relatively easily. We get something like x squared plus 2xy plus y squared. That would be the first two. And then those two concepts would have to be multiplied by the foiling of the other two, which would be x squared plus 2xy plus y squared. Now this starts to get really tedious because we've got to do 3 things, and we might end up have done, I don't know, maybe you might have Miss Babbitt, or you had Mr. Worthen, or some other crazy people, and they made you put it in a matrix like x squared, 2xy, and y squared, and this one's x squared and 2xy and y squared, and you'd fill in the interior 6 boxes, and you'd get something like x to the 4th. Boy, that thing's huge. We don't want to use that. X to the 4th, and then this would be 2x to the 3rd y, and that'd be x squared y squared right there. This one would be 2x to the 3rd y. This would be 4x squared y squared, and that would be 2xy squared. And then the final one would be x squared y. This would be 2xy squared. I know you're trying to follow along. There's a lot of them here. And then y finally to the 3rd. Ooh, that would be a squared. Sorry, I got to make sure I get this guy right. 2x squared, y squared, 2x to the x squared, y to the 3rd. And this would be y to the 4th. Now, all those ones that are interior right there would be the ultimate answer. X to the 4th, because there's none like that guy. Okay, the x to the 3rd y's, looks like there's 4 of those. 4x to the 3rd y. And then that'd take care of these two. These should all be in the same column along with each other. So it'd be a total of 6 of those. 6x squared y squared. That takes care of this row or diagonal. This one right here would be another 4xy to the 3rd. And that would be finally on the end, y to the 4th. And you're like, whew, that was a lot of work. Okay, and you're right. That actually turned out to be kind of a pain of what you were doing right there. And ultimately, if you had to, for some reason, do that kind of concept a little bit further And if you had to go further than that particular concept, you'd be like, forget it, I'm not going to do it. Now, that's exactly how most mathematicians felt about this concept too as well. But if we had to expand something, then we would want something a little bit cleaner that might be able to give you the possibility to expand it. Now, that is where this next concept comes into play. This is what's called the binomial, and sometimes they call it the binomial theorem, or they'll sometimes call it the binomial expansion theorem. Now, what this allows you to do is it allows you to take binomials that are relatively higher power orders and find a way to expand their particular expand their abilities into this larger polynomial concept. Now, you're probably asking, what the heck does this have to do with sequence and series? Well, first off, let me talk to you about the series question. The series question is where we talk about this all being a sum. And ultimately, when we expand the binomial that's going on here, it really does end up turning out to be a sum of several different digits, all these individual sums going down the line. So it does have a series concept. Now, the part you're going to ask is, where is the sequence part to this? And the sequence part to it actually pertains to how the coefficients, one, are related as they go into the particular down, and then the second one on how that one is perceived to be going in an upwards direction. So there's kind of this sequence going on right there. And then there's also a sequence that we don't really see much, but these numbers in the front represent a sequence of their own. Okay, and that is why we start to discuss these concepts in chapter 10 too as well. So it's all about sequence and series, but it's going to look something like this. Now, the binomial expansion theorem, if I wrote it out by definition, turns out to be written as a summation. And if I write it as a summation, that summation is going to start from k equaling 0. This is going to be strange because we don't normally start our k's or i's from 0. And it'll go to n. And that n is going to be the number in this top part right here, the power that we're going to do. So if we're going to raise something to like a 6th power, we're going to go from 0 to 6. Now, to make the sequence in terms of its summed pieces, there's going to be a piece that's going to represent the coefficient in the front. And then we're going to have to figure out what should we put in these two places that represent the variables in each individual term. Well, this variable is going to be x raised to the n minus k, and this one is going to be y raised to the k. And what that's basically going to do is that this first n value, what I would say was a 6, it would be 6 minus 0. This one would be raised to the 6th, but this one, since we're on the 0th term, would be 0. And then the next one down the line, this would go up to 1. That'd make this one 1. But this one would go down to 5. And you get this consistent that one's going down and the other one is going up. And that's what that concept is going on right there. Now, the real question is, how do I come up with this little sequence coefficient that goes in the front? Now, this is going to be generated by, and I'm going to put nk in parentheses like this. This is the notation for it. But what that notation is standing for is this over here. It's standing for what's referred to as a combination. A combination. Okay, no, I didn't get a spelling certificate. I got a math one. Now, you're probably confused, like a combination? What is a combination all about? Well, it turns out that combinations were discovered by Pascal, and Pascal found out that he was kind of like, maybe he was sitting down one day and he was thinking about how to choose from different objects. Maybe they were rocks. I don't know what they were. And he basically said, if I was stuck with no rocks whatsoever, I'm going to call this row 0, I had no rocks whatsoever, how many different ways would I be able to choose nothing? Okay, now that's bizarre. There's only one way to choose nothing at all. Okay, so if I had nothing, you only can choose nothing one way. Now, that's going to seem stupid, But what if I actually said that instead of having zero things, I had one thing? Well, if I had the rock in front of me, I could either choose to not choose the rock. That would be one way to not choose anything. Or I could choose the rock that's in front of me, which is there's only one rock, so one way to choose it. Now, that particular this way of thinking about combinations doesn't really make a lot of sense yet, but what Pascal did is he started to see these combinations and started to see a pattern that was associated with those particular combinations. Now, let's say we were talking about two objects. I don't want to say keep talking about rocks, but if you had two rocks in front of you and you chose none of them, there would only be how many ways to choose none? Oh, well, there would only be one way to choose none of them. Okay, I'm not choosing any. But the moment that I said I wanted to choose one of them, now there's two different guys in front of me. So I'd be like, okay, well, there I could choose a guy on the left or I could choose a guy on the right. Well, there would be two different combinations that you could do. Now, as soon as you got over here to the far side and you said, hey, I have two things, but I want to choose two of them, that would be only one way. Now, each one of these is represented by a little combination notation. This row right here was two objects, and I was choosing in that particular spot right there, none of them. Where this one was I had one object, and I was choosing none of them. That's why that combination turned out that way. This particular guy right here was two, and I was choosing one at a time. That's why that's two, choose one. This would be two, choose two. I have two objects, choosing two of them at a time. Now, I'm going to go to the third row before you really start to see the pattern that Pascal found right here. Now we're down to three objects. Okay, now what would those three objects be? Hold on. I got to erase a little bit here so I can make myself room. I keep getting too close. Row 3. Okay. I say, hey, I have three objects, choosing none of them. Well, that makes sense. I can only do it one way. But if I got down here to the next one, right here in this spot, I would be like, okay, I have three objects and I can choose one of them at a time. Well, that would be three different combinations, or three, choose one. Okay. This combination next here would be I have three different objects. I can choose two of them at a time. You could do like the first and the second and the third, or the first and the third. Oh, there'd be three ways to do it. That's three, choose two is what that would be. And then if I had to choose all of them, it would be three, choose three, and there's only one way to do that. Now, what Pascal saw here is he started to look at these individual numbers, and he was like, okay, I'm going to take the combinations out of there and look at the numbers that are going on there. And he developed a pattern that looked out of it. And this is what's referred to as Pascal's triangle. Now, Pascal found out that if you put them in such a structure, the two that are above the one diagonally add to the one that goes below it in between. These two add to the one that goes down below that one. Okay, so if I wanted to make the fourth row always starts with a 1 on the far side. That would be 4, choose 0. Okay, then I could make the ones in between relatively quickly. This is 4, this is 6, this is 4, and this is 1. The one down here on the end being 4, choose 4. And that's row number 4. Okay, now this little Pascal's triangle can be really helpful, especially if you know it down to at least, down at least to probably the 6th row. That's probably where we use it the most often, is down to the 6th row. So let's draw it out. So you got the idea. Here's 5th row. That's 1, 5, 10, 10, 5, 1. That would be for row 5. Okay. And then the row 6th one is 1, 6, 15, 20, 15, 6, 1. Now, the reason why I keep bringing up these combinations in terms of what's going on there is Pascal noticed that in the binomial expansion up here, that the numbers that were inside of the deal here were a 1, a 4, a 6, a 4, and then a 1. And those particular ones in that order represented, check it out, row number 4 of the combinations. And that's why we can put this combination notation into our sigma to generate the coefficients that go in front of our individual binomials. Now, the only way to really get good at the binomial expansion theorem is to practice it a couple of times so that you can get the idea of what's going on. Now, I will get somebody who will say, Mr. G, that's only a fifth power. Why can't you let me do it FOIL? And I will say to you, go right ahead if you want to. But by the time you finish with your expansion and FOIL, I'll be done with this problem and moving on to the next one. And you'll be left way behind. And then when I get down to number example 3, you're going to be way, way behind. And I'll have broken you very, very easily. Now, what I want to think about is about what the binomial expansion says these are going to end up becoming. Well, they're going to end up being individual terms all the way listed down the line, and you're going to have coefficients that go in the front of them. So I'm going to first draw a starting point right here. I'm going to say, okay, I'm going to say that there's going to be a coefficient that goes inside this one. I don't know what it is yet, but I'm going to figure it out in just a second. Now, the other parts of the binomial expansion that it'll be is it'll probably be an x and it'll probably be a y in relationship. Now, what we saw in that one previous is that the powers on the first part of the binomial expansion will be relatively high to start, and the 1 second will be relatively low. And you're not wrong. What you're going to do here is you're going to apply all the power to the very first one. This is where all the power will end up being. And then on the second one, you will put no power on it at all. Okay, now what's going on here is that this still adds up to the fifth power. Remember that addition of exponents concept that's going on. Now that's going to be the very first term, way it's going to turn out. The next one is going to have a coefficient on it, but when we get the x and the y, the x part is going to go down. That's what that sequence is going to do. So this is going to be to the fourth power. But the y, its sequence on its power is going to go up. But these two numbers will still add to 5. It'll be all the different combinations of 5 that we can get in the variables. Now I'm going to keep drawing these. That's going to be x to the third and y to the second. X's are going down, y's are going up. Then this is going to be x to the second and y to the third. This would be all those diagonals you would be adding in the matrix style. And then we would get another one. Oh, that's x to the first, and that's y to the fourth. And then down here on the end, it's going to be x to the 0 and y to the fifth. And I've gotten every combination that the powers could turn out to be in terms of the exponents. They have to add to 5. Okay, now you're probably like, oh, okay, that seems pretty reasonable. Now the question is, what goes in the blanks? All right, sorry for the blank space there. It's just this thing freaking me out sometimes. Okay, now what should go in those blanks? What should we put there? Well, it turns out that what goes in these particular blanks is what we were talking about inside that sigma that ended up being the N, O, N, and K concept, which was the combination concept. And that combination that we're going to deal with right here turns out to be the fifth row of Pascal's triangle. So really what's going in this spot right here is 5, choose 0. That's that very first one in Pascal's triangle. Now that's the reason why we wrote it in that other section, is that Pascal's triangle row right there could be really super helpful. And it turns out that 5, choose 0 is 1, and this is 5, and that's 10, and that's 10, and that's 5, and that's 1. And that's exactly what the coefficients would have turned out to be if I had gone ahead and done this whole entire thing foiled out. Now, the one thing I do want to point out is as we write these out, most of them are usually all plus, but then there's this little guy right here about the minus sign. And what that's going to do is instead of everything being positive, like it would be if it was positive. We were just multiplying positive values. This causes an alternation. You end up alternating signs is what's going to go on here. And it turns out that the first one is always positive that you end up doing for the alternate, unless you had a negative out there. But this is going to cause an alternating sign on the second term, and it just alternates signs as it goes down the line. And that is your binomial expanded. That was what it'll actually turn out to be. Now, you're probably looking at it like, oh, all right, that's not too bad. It's way more doable than the stuff that we've been seeing in probably foiling it, but it can end up having a little bit of quirkiness that's associated with it. So let's kind of talk about some of the quirky nature based on how this will boil down. Now, first off, this is going to be a sixth power binomial expansion. So I know we're going to be using probably the sixth row is what we're going to be talking about. And there's going to be a couple other things that are going to come into play. And that specifically is this number 2 that's listed here. Now, I'm going to tackle it just like I did before. And I'm going to put in the coefficient just like I normally did. But when I did this upper piece, I did x and then I did y and then I did the powers on it. Now I'm going to stay with the same idea, except that this is going to be a 2x and a y, and I'm going to distribute the powers on those. Now the first one starts out as 6, and this one starts at 0. And ultimately, that's the combination that we're going to continue to keep going with down the line. That's a 2x, that's a 5, that's a y to the first. This one's going to end up being a 2x and a 4 with a y to the second power. And again, all these powers are still adding up to 6 up above. Now, you might end up running out of room, but you got to kind of keep going with it. 2x and to the third, y to the third, and you're like, oh man, there's a lot of these guys. Okay, keep going. That's a 2x, and that one's going to be raised to the second power, and this is going to be y to the fourth. And then this one's going to be a 2x and to the first power and a y to the fifth power. And down here on the end, it's going to be 2x raised to the 0 power and y to the sixth. Now, I know there's somebody out there going, gee, man, those 0 power ones are really not necessary. And you're absolutely right. This is going to be the number 1, and it ends up becoming irrelevant in those particular regards. So does this one, turns out to be a 1, and it's really just y to the sixth on the end. Now, the coefficients that go in the front of these turns out to be the sixth row of Pascal's triangle. Or better yet, this one should be 6, choose 0, which is 1. And this one right here would be 6, choose 1, which is the number 6. And down the line for sixth row of Pascal's triangle. Now, I don't memorize them to that idea, but I can kind of get it from the one above. That one's 6. Oh, this one's going to be a 15. This one's going to be a 20. This one's 15 and 6 and 1. And they go up and then they come back down is the way that those particular values work. Now, you're probably like, oh, right, I got this thing completely licked. Except for the fact that when we write these terms out, we have to make sure that we're consistent with what every term's going to be. Now, you're agreed that it's a 1 right here, but this sixth power is not just going to apply to the x, it's going to apply to the 2 in front. Now you're starting to see what those coefficients really did end up causing to happen. So I'd really have to think about, okay, that's really 2 to the sixth power, but then that answer 2 to the sixth is going to be multiplied by 1. So this front term is going to be 64x to the sixth. Now that's your very first one. Plus, now we've got to evaluate this guy. Well, that fifth power is going to apply to the x for sure, and it's going to apply to the 2. So I'm back to my calculator. That's 2 to the fifth, and that answer is going to get multiplied by the Pascal triangle combination number times 6, because that number does come into play, and this will be 192x to the fifth y. Okay, now you're starting to see that the coefficients on the binomial itself, they do come into play. Okay, so next guy. Ooh, what do I got there? 2 to the fourth. And 2 to the 4th is, oh man, I got to do that one. 2 to the 4th power is 16, and then that 16 is going to be multiplied by 15, and I'm going to get an answer of 240. 240 x to the 4th, y to the 2nd, and that takes care of them. Now, what I've usually do in the past is like, once I get one done, I'm like, ugh, cross it out, so I know I've done those, and I can keep working my way down. 2 to the 3rd power is 8. 8 times 20 is 160. So 160 x to the 3rd, y to the 3rd. And they get a little bit easier as I go down here. 4 times 15 is 60. So that's 60 x to the 2nd, y to the 4th. And then I've got 12 x, y to the 5th. And then down here on the end is 1 y to the 6th. Ta-da! I got myself a binomial that's completely expanded. Woo! That was awesome. Okay, no, you're probably thinking that wasn't very awesome. Okay, now the next one, I'm not going to probably set up the entire thing because ultimately it can get a little bit out of control. But what I want to do is at least set up what the functions would be. So I've got a coefficient, which is waiting for a 5th row Pascal's triangle. Then it would be a 3x raised to the 5th and a 2y raised to the 0. Now be careful, you're going to maybe want to write yourself here an alternating sign memo because of the negative. Notice I didn't put the negative inside here. It's not really necessary because the alternating sign concept will take care of it in the end. Now the next one would end up being 3x raised to the 4th, and the 2y would be raised to the 1st, and this would be the second value in Pascal's triangle. So ultimately, I think the 5th row is 1 and 5. And then it'll be dot, dot, dot down the road. Now, these first two terms would end up being 3 to the 5th power, which off the top of my head, I don't really remember. So what do we got here? 3 to the 5th power. And I'd get 243. Now, this is going to generate a 243x to the 5th. This is 1 because it doesn't make any matter. So 243x to the 5th would be the first term. Now, the next term along the line would be a 3 to the 4th power and a 2 to the 1st power and a 5. So I'd want to multiply all of those three things times each other. So a 5 times a 3 to the 4th, and then times a 2 in the that third part there, and it'd be 810 x to the 4th y. Now, this one is going to be based on alternating signs. That one would be positive, and then this one would be negative, and so on down the line as you continue to expand that binomial. Okay, as I was going down it, maybe I'll do one more just here so you could see it. It'd be a coefficient, a 3x raised to the 3rd power, and a 2y raised to the 2nd power, and this would be the number 10 in Pascal's triangle. That's going to give you a 27, that's a 4, that's a 10, blah, blah, blah. You get the idea, right? But just keep in mind, it's going to be every coefficient if there's a coefficient inside there, and this next term would be positive because of the alternating sign idea. So it's about being systematic and being consistent. Now, other than being able to write the whole entire tamale, write the whole tamale out, what if you wanted to zip to a specific term? What if you wanted to go to a specific term in the expansion? Like, say, I want the 5th term in the sequence. So you're kind of like, I'm going along down the line, and then I'm going to get to a coefficient that's at that spot. I'm going to get an x that's going to be raised to a certain power and a y that's raised to a certain power, and then I'm going to be down the rest of the line. Now, how am I going to be able to zip into this particular spot? Now, I know this is a 5th term of a 12th row. We don't have any 12th rows written out. But let me just say, what if I was trying to find maybe a simpler problem? Maybe let's go something simple. And I was trying to find, say, like the 3rd term of a 5th of a 5th row of row 5. Let's put that row 5. Now, if I was going to write row 5 out, you'd probably recognize that this is a 1 and then it's a 5, and then it's a 10. And that would be the third term in, right? This would be, recognize the coefficient of the third term. But what I want you to realize is that this was 5 choose 0. And even though it's the first term, it's the choose 0 combination. And this is 5 choose 1, and it's the second term of the situation. And this is 5 choose 2, and that's the third one of the deal. Now this is the combination. What should go here? Well, it shouldn't be 12 choose 5, because the series starts way out here with 12 choose 0, and that's the first term. This ultimately better be 12 choose 4. That would be the fifth term in to that particular row of Pascal's triangle. Now that's a pretty solid deal right there. You're like, wow, 12 choose 4. Now that's a way for me to write it. Is there a way for me to find it? And the answer to that is yes. I'll show you in just a second. Now, what would the powers be on these as I was going to? Well, this one right here would be x to the 12th and y to the 0. And that works on the same premise, the 0 concept, as the choose value down below. It turns out that whatever the choose value is right here, that's the power on the second guy. And it's going to be the same power as that what you're choosing for. Now, what should be the power on the other exponential? Well, the key is that it's got to add to 12. And that means if this one's already got 4 on it, this one's got to be 8. And now we're searching in. We've got a place where the fifth term would be. Now, what we need to do is come up with the coefficients. I know the answer is going to be x to the 8th and y to the 4th, but what goes right there? And this is where your calculator comes in and can really help you out. Can it find the fifth term of Pascal's 12th row combination? And it can. Here's what we're going to do. We're going to go to our math key, and it's on the math key, but it's going to be back over here under probability again. And you can probably see an NCR concept that's listed right here. Now, it's going to need input for N, and it's going to need input for R, and it depends on your operating system. My operating system doesn't allow me to put any things in. If it shows up like that, you have to put the number first, then choose math, probability, NCR for choice. That's your choosing. And then you go 12, choose 4. And it'll tell me that the answer is 495. And that's how you come up with a combination off of your calculator. Now, if you're one of those people that doesn't have your calculator with you right now, you can easily do the same concept off of Desmos. And I'm going to go to Desmos for just a second. And I'm here in Desmos right now. And Desmos has that combination button too as well. You just got to dig a little bit for it. It's underneath functions down here in the bottom. And it happens to be under stats. And you don't want to pick the COVID button. But right below that one, you want to pick NCR. And it'll put a little NCR deal up here in the top. Now, what it's asking for is for some inputs. And you want to do 12, comma, choose 4. And it'll tell you what the number is off of Desmos just as easily. All right, so combinations can be done there as well too. All right, now we'll go back to this particular deal. Now, let's try it again. Let's see if we can come up with where we're going to be. Ninth term of a 15th row Pascal's triangle. And then we're going to be like, I'm down to the ninth term. Right there. It must be 15, choose. But remember that guy out there in the front was 0. So this would be 15, choose 8. W and Y are going to be comboed here. And again, this number is going to be the same as the choose category. And this one will be the one that balances out the power. So W to the 7th and Y to the 8th. And then you keep on down the line. Now, here's a quick question. What about the negative? Now, let's get to that negative in a second. It's an alternating concept, and you're going to have to figure out how the alternation works. And let's try and figure out what 15 choose 8 turns out to be. Well, 15, math, choose, let's try it again, choose 8, happens to be 6435. So it's 6435, W to the 7th, Y to the 8th. Now, that is the term that's going to be in the ninth place. But the question is, should it be a plus or should it be a minus? Now, there's an easy way to tell on these alternating ones what the plus or minus will be. I'm going to go up to this other one that was a plus or minus, had a minus right there, and it started out plus, and then it went minus, plus, minus down the line. It actually turns out that the first term is plus, the third term is plus, and the fifth term is plus. And it turns out that odd ones are positive for odd terms, and negative for even terms. So in this particular case, since we're looking for the ninth term, that's an odd term, it better be plus. And that's what it'll be as we go down the line. Okay, pretty straightforward, easy thought there. Now, what if there are coefficients that get involved in this particular process as well too? Seventh term, okay, I'm dealing with that. 12th row, okay, must be 12 choose 6. That's the number that's going to be one less. You can always think of it as the n up there as n choose, and then it's going to be the term that you want minus 1. So I'm going to be like term minus 1. That's what choose will be. And then it's going to be 2a raised to something and 3b raised to something. It looks like a 36. 3b raised to something. This is going to be raised to the 6th power. That would mean that this term right here, y power, is going to be raised to the term minus 1. And then this one right here is going to be the n minus the term, or n minus t minus 1. I don't know if this is the easiest way to think about it. I don't know. I don't like that formula. I just think balancing it out makes more sense. So this is 6. This one would be 6. All right. I don't like to confuse it if I can't. All right. Now, watch out. Okay, little star right here. It is an alternating one. We'll have to keep that in mind. So we got to think plus or minus. We don't know which one it is. Let's see what we got here. Well, 12 choose 6 is just a number. Let's see what we got here. 12, math, choose 6. And I end up with 924 for this piece. But remember that this 6 is going to apply to that too. So it's really going to be a to the 6th here, but there's going to be a coefficient in front there, and that's going to come into play. So let's see what we got here. 2 to the 6th power happens to be, I believe, 64. So this is going to be 64 a to the 6th, and 3 to the 6th. Oh, I don't know that one off the top of my head. 3 to the 6th is 729, with b to the 6th written on the top of that one. Now, all these numbers in the front, they're going to have to get multiplied. Holy moly, that's going to be big. 729 times 64 times another 924, and that would be 43. Uh-oh, it disappeared before I could write it. 431101, 1101, and then one more time. 44, or better yet, 43,110,144, a to the 6th, b to the 6th. That's hilarious. Now, you're probably going, gee, that's asinine. Yeah, it actually kind of is, but it's really cool to see that the patterns that we've been discussing really do end up coming into play. You can expand anything you wanted now. Now, it's an alternating sign, and it's an odd one, and odd terms turn out to be positive, so this would be a positive value that you would get in the end. Okay, now that's the 7th term. There's a whole lot in front of it, there's a whole lot behind it, but I was able to zip to one specific term in the sequence. Okay, now I'm going to let you try one on your own. Here's your try concept. So pause the video and give this baby a try. And the magic never ceases to amaze me. We tried that, and here's what we basically came up with. 16th row of Pascal, 12th term, 16 choose 11. Now that's key right there. Make sure you do that part right. The 11th power on the 2nd term. Notice that the y and the x are out of order, but they're out of order in the polynomial, or the binomial anyways, so just keep them in whatever it is. But variables are variables. They could be smiley faces and pirate ships. Who cares? Okay. Make sure you balance the power and what's going on there. Through a 4368 is 16 choose 11. 3 to the 5th power is 243, and there's no coefficient on the x, so that's kind of nice. And it ends up 243 times 4368 is 1,061,424, and that would be y to the 5th, x to the 11th, and it would be a negative because it is an even term and it's an alternator. So it turned out to be a negative value in that particular case, okay? Now, the key to these is a little bit of practice, guys, and Math Excel has got that put together for you. I know you're going to be extremely successful in this one. It's really not hard material. And I really want a big shout out to all you Huskies out there who have been doing your digital learning and learning some new stuff, because Pre-Cal is key to being successful in calculus. Now, our upcoming units, when we move to chapter 11, is going to be even more important. So stick with this, guys, and keep crushing it. You're doing great. G out.